Welcome to this explainer. Today, we're cracking open a really fascinating chapter of mathematics. We're looking at how theoretical probability acts as this elegant, almost magical shortcut for predicting our totally unpredictable world. Have you ever wondered how experts actually calculate the precise risks of massive events without doing endless trial and error? Well, the answers are hiding right here in the formulas of this chapter, literally translating pure uncertainty into cold, hard numbers. Okay, so here's our roadmap for the explainer. First, we'll look at moving beyond trial and error. Then we'll dive into the classical probability formula, explore the power of not, map out impossible to sure events, and wrap it all up with probability in the real world. All right, section 1, beyond trial and error. Let's talk about moving past repetition. For a long time, humanity totally relied on experimental probability, right? Like, if you want the odds of a coin landing on heads, you just flip it 1,000 times. Easy. But how do you figure out the probability of a multi-million-dollar satellite failing during launch? You obviously can't repeatedly crash expensive rockets just to tally up the empirical odds. And you definitely can't trigger hundreds of earthquakes just to see how often a building collapses. We absolutely needed a better way. And that is exactly why this chapter transitions us from physical, real-world repetition straight into theoretical probability. It completely bypasses all those messy physical trials. Instead, it relies purely on logical assumptions, specifically assuming that outcomes are equally likely. This gives us an incredibly accurate answer almost instantly, just through deductive reasoning. It's a total game changer. Moving right along to section 2, the classical probability formula. Let's get into the theoretical side. The absolute greatest single contribution to this foundational branch of math came from this man right here, Pierre-Simon Laplace, way back in 1795. He's the one who formalized the theoretical approach, handing us a tool that we literally still use today for everything from mapping genetics to predicting the economy. And you know what? Laplace's elegant formula is wonderfully simple. The theoretical probability of any event, let's just call it event E, is simply the number of outcomes favorable to E divided by the total number of all possible outcomes. Now, there is one absolutely crucial assumption holding this whole thing together. Every single outcome must be equally likely to happen. Let's actually look at how this works in practice. The main thing here is identifying your sample space. Say we throw a standard fair die. Our total possible outcomes are just the numbers 1, 2, 3, 4, 5, and 6, right? So our denominator is 6. Now, what if we want to find the probability of rolling a number strictly greater than 4? Well, we just hunt for our favorable outcomes. In this case, only rolling a 5 or a 6 satisfies our condition. That gives us exactly 2 favorable outcomes. 2 divided by 6 simplifies perfectly to a 1/3 probability. Boom. Instantly calculated, and we didn't have to throw a single die over and over again. And the best part is, we can scale that exact same logic way up. Take a standard, shuffle deck of 52 cards. If we draw just one card at random, we have 52 equally likely possible outcomes. But what if we want to know the probability of drawing an ace? Well, we know for a fact there are exactly 4 aces in a deck. So, 4 favorable outcomes divided by 52 possible outcomes simplifies down to a 1 in 13 chance. The logical framework holds incredibly strong no matter how large your finite sample space gets. Okay, on to section 3, the power of not. This is where we talk about complementary events. So, sometimes calculating the probability of an event directly is just way too exhausting and complex. When that happens, we use what are called complementary events. This builds on a really strict fundamental rule. All possible probabilities in an experiment must always add up to exactly 1. Because of that, the probability of something not happening is simply 1 minus the probability that it actually does happen. Let's apply this to a really famous puzzle from the text. Imagine 2 friends, Savita and Hamida. What's the probability that they share the exact same birthday? Figuring out the odds of every single matching day directly is a total nightmare. But if we use the power of not, we can take a massive shortcut. Let's just find the probability that they have different birthdays. If Savita is born on one specific day, Hamida has 364 other days to have a different birthday. That gives us a 364 out of 365 chance. We take that fraction, subtract it from 1, and just like that, we reveal a 1 in 365 chance that they share the exact same day. It's just a beautiful mathematical shortcut. All right, section 4, impossible to sure events. Let's test the absolute limits. What happens if an event literally cannot happen? Think back to our standard 6-sided die. What is the probability of suddenly rolling an 8? Well, because there are exactly 0 favorable outcomes for that on a standard die, your numerator is just 0. And 0 divided by 6 is 0. So, in theoretical probability, if an event is entirely impossible, its probability is precisely zero. No way around it. But conversely, what if an event is absolutely guaranteed? If you roll that very same die, what's the probability of rolling a number less than 7? Well, since all 6 faces display a number less than 7, you've got 6 favorable outcomes out of 6 possible outcomes. 6 divided by 6 is 1. When an event is completely certain to occur, we call it a sure event, and its probability is exactly 1. And this right here reveals our ultimate mathematical boundary. Because favorable outcomes can never be less than 0, and logically they can't ever exceed the total number of possible outcomes, probability is strictly confined. It can never be a negative number, and it can never be greater than 1. Every single calculated risk out there is trapped squarely between 0 and 1. Finally, Section 5, Probability in the Real World. Let's talk about continuous probability. Up until now, we've only dealt with finite numbers, 6 sides of a die, 52 cards in a deck. But a lot of physical experiments, like predicting exactly where a falling object is going to land or precisely when a spinning wheel will stop, well, those have infinitely many microscopic outcomes. We can't just count whole numbers anymore because there are literally infinite points in physical space. So how do we adapt Laplace's logical formula for that? Well, we adapt it by swapping out the number of outcomes for the measurement of area. Take this crazy scenario from the chapter. A missing helicopter crashes somewhere within a rectangular region measuring 40.5 square kilometers. That entire area is our total sample space. But inside that region is a lake measuring 7.5 square kilometers. We just divide the favorable area, which in this case is the lake, by the total area. 7.5 over 40.5 gives us exactly a 5 in 27 chance that the helicopter is submerged in the water. It is pure geometry, calculating messy, real-world risk. Or, consider massive-scale commerce. A buyer randomly pulling a shirt from a bulk carton really needs to know their inventory risk. If a carton of 100 shirts contains 88 perfectly good ones, 8 with minor defects, and 4 with major defects, a trader instantly knows their sample space. If they only accept flawless goods, they know immediately they have exactly an 88 out of 100 or 88% chance of pulling an acceptable shirt completely at random. The math literally allows businesses to model their financial risk entirely on theoretical ratios, rather than wasting time inspecting every single item first. So what have we really uncovered in this chapter? We've seen that theoretical probability is a genius shortcut to understanding reality. From Laplace's very first equations to mapping out geometric crash zones, math lets us put a frame around the unknown. But as you navigate a world that is fundamentally shaped by these invisible mathematical ratios, it kind of leaves you to wonder, what hidden probabilities are quietly dictating the major choices in your own life? Thank you so much for joining me on this explainer. Keep questioning the odds, and I'll see you next time.